Okay, so to start, I would like you to imagine yourself at a party, okay? Somebody comes to you and they ask you, what is your job? You know, for me, during the last 8 years, my answer was, I'm a researcher in quantum computing. And the reaction was always like, they look at me and they're like, oh, wow. So are you like Sheldon from Big Bang Theory? And while in a way that is flattering, what is really telling us is that people are really intimidated by the word quantum. They hear quantum computing, they get scared. They think of a very high level, very academic field. So today I want to challenge that. I would like you to start embracing quantum computing. Let me tell you why. So computing power has been the engine of modern economy for roughly the last 80 years. And the idea is simple. We believe that every year we have more and more computing power into smaller objects. So look at this photo. This is Cray 2. This was the most powerful computer in 1985 on Earth. The interesting thing is that machine is as powerful as an iPhone 4, not even the latest model, as an iPhone 4. So this concept of more computing power into smaller systems is very well captured by Moore's law. What Moore's law does, it predicts that every 2 years, the computing power doubles. Can this continue forever? The answer is no, it cannot. Why? There are fundamental limits. And these fundamental limits are natural, are physical. If we keep on miniaturizing objects more and more and more, at some point we enter into the world of quantum physics, of quantum mechanics. And then the laws change, and the rules of the game change as well. Okay? This idea was very clear to the great American physicist Richard Feynman. In 1981, Feynman, at an iconic conference organized by IBM and MIT, he went on stage and he said something very profound. He said, if we want to be able to simulate any physical process, we need to build a device that speaks the same language as nature. And the language of nature is quantum mechanics. And the device is known as a quantum computer. So I want to give you a little bit of intuition on what is the difference between a quantum computer and a classical computer, the computers we are used to work every day. I really like this analogy. So think of computation as a process that takes you from point A to point B. Okay? If you have enough time, you can drive from A to B. And then think of it as using a laptop. If you want to get to point B much faster, then you can take a plane. And then think of the plane as a supercomputer. But there is a problem. If point B is on the moon, then neither a car or a plane can take you there. So you need a rocket ship. And a quantum computer is a rocket. And this is the intuition, right? It can take you to places the classical computers can never reach, no matter what. No matter how powerful a car is, it cannot go to the moon. Let me be a little bit more specific. There won't be too much math, I promise, but just a little bit more specific. So a classical computer works by processing information encoded into bits, okay? And bits are just switches, either 0 or 1. Quantum computer works similarly, but instead of having bits, it uses quantum bits, also known as qubits. How do we visualize these two things? So imagine we are on a planet, and I want to encode information depending on my position on the planet. If the planet is a classical bit, I can only be at the North Pole, a 0, or the South Pole, a 1. But if the planet is a quantum bit, I can be anywhere on the surface. And this is a concept known as superposition, quantum superposition. You might have heard of it when you hear people talking about the Schrödinger's cat. It's dead and alive at the same time. So when I'm not at the poles, I'm in a superposition of 0 and 1, a little bit of 0 and a little bit of 1. And this should already give you the intuition that quantum computers can do more than classical machines. One of the great consequences of superposition is that when I consider a classical computer, if I have a string of bits, that machine is exactly in one state at each and any time. So for example, here, in the last example, I am in 0, 1, 0, just one state. But because of superposition, this is not true anymore in quantum computers. Now I have access to more states at the same time, something known as the exponential growth of the Hilbert space. And this is one of the reasons why quantum computers are believed to be more powerful than classical machines. Okay, this is really exciting. But why don't we have a quantum computer on stage? Why we are not using a quantum computer now? Because they're really difficult to build. So if you look at this photo, which is beautiful, this is the IBM quantum processor. And what you're looking at, really, is a big, expensive refrigerator. So why do we need a refrigerator? Because when I speak about qubits, I'm speaking about physical systems. And to build a qubit, you need to use quantum systems, subatomic particles, maybe a photon. And these particles are very hard to control. It's really difficult to use them to perform computations. And then you have this big fridge because you want to cool down the system to temperatures that are colder than outer space. And this is when you can start to exploit the quantum effects and do meaningful computations. There are good news, though. If we take the number of qubits as an indication of how powerful a quantum computer is, in the last 3 years, we have seen astonishing progresses. Rigetti Computing, which is a leading quantum hardware startup in the space, just announced a few weeks ago that they want to have a 128 qubit device by the end of next year. And with that many qubits, we might be able to do something that a classical computer will never be able to do, a concept known as quantum advantage. Another really positive message that we get from this graph is that the number of qubits has been roughly doubling every 6 months, much faster than Moore's law. This is really exciting. So quantum computing really feels much, much closer to that. Okay, but what do we do with quantum machines? What do we do with quantum processors? So I'm the founder of a company called Entropica Labs, and we are really excited about using quantum computers to solve some of the hardest problems in bioinformatics. Let me tell you why I believe the whole field of biology will really receive a boost from quantum computing. So this is a molecule, and I'm sure all of you are very familiar with it. You see it every morning when you wake up in your mug. This is caffeine. This is a molecule of caffeine. And by biological standards, this is actually a pretty simple molecule. It's not very complicated. And yet, if you were to simulate that molecule using a classical computer, it would require 10 to the 48 bits, roughly, which is a huge number. If you think about it, on planet Earth, there are about 10 to the 50 atoms, which really implies that you would need to use 1/100th of the planet to simulate just the molecule for caffeine. But when it comes to drug development, when it comes to new medicines, the kind of compounds have thousands of atoms. You simply cannot simulate them fully with a classical computer. We need to go beyond. We need a quantum processor. And the good news is that if we had access to a quantum computer with few hundred of clean qubits, which means qubits without any error, we could simulate these molecules. This is really powerful. Another fantastic example of what quantum computers will be used for was given by the Microsoft team. So at Microsoft, they said, OK, consider nitrogen fixation. Nitrogen fixation is a process that gives us ammonia. And ammonia is extremely important today because it's the most used fertilizer on the planet. One of the reasons why we can feed billions of people today is because we can produce ammonia. There's a problem, though. The chemical reaction of ammonia, of nitrogen fixation, is really hard to study with classical computers. It's impossible in practice, which means that the process that we use today is highly inefficient. It consumes a lot of energy. But with a quantum computer, we could find better catalysts and dramatically reduce the amount of energy needed to produce ammonia. Think of the opportunities. Now we could produce more and more food. This is a really powerful message. We at Entropica are very excited about using quantum computers for genomics analysis. So in genomics, what you want to do, you want to find connections between genotypes and phenotypes so that you can start developing very precise therapies that are tailored to each person's DNA, something known as precision medicine. But this is hard to do. You're looking for correlations in very messy data. Think of pattern recognition. Think of unsupervised machine learning. Very difficult task computationally. We believe quantum computers will dramatically boost that. And the message here is simple, but really powerful. Quantum computers are going to solve the kind of problems that are fundamental. They will help us to understand more and more about nature. They will really unlock what are the core messages hidden in nature by helping us to understand more and more about the quantum mechanical effects, especially in biology. To conclude this little section, I want to invite you to think that quantum computers will really change the way we perform computations in three main areas: quantum simulation, quantum machine learning, and quantum optimization. So now I want to start inviting you to think more and more quantum. Why? This might still sound a little bit intimidating. Maybe it still makes you a little bit lightheaded, but it shouldn't be. There are a lot of resources out there where you can start actually using real quantum devices today over the internet. IBM was the first one. They introduced the IBM Quantum Experience, which is really exciting. You can use their devices for free and have access to a 5-qubit processor and a 16-qubit processor. Rigetti Computing, just 1 week ago, on Friday, announced the Quantum Web Services, which is a quantum answer to Amazon Web Services. They want to have a structure where classical computers and quantum computers will work closely together to start solving real-world problems. The very exciting thing about the QWS is that Rigetti announced a partnership with 12 leading startups in the field, and we at Entropica are one of them. It's really exciting. Xanadu is another hardware company. It was launched by a friend of mine, Christian Whitbrook, and they are building quantum computers using a different technology that is not based on qubits, but is based on something known as Q-mods. But again, the message here is you have no excuses. You can start using the devices today. You have tutorial online. You can really start playing with real quantum computers, something that most people are not familiar with. Think of the job opportunity. In the US, every year, there are more than 2 million openings for data analysis jobs, which is a very crowded space. The same will happen for quantum computers, and we don't have the talents. On the planet, there are around 10,000 people who can work with quantum computers. It's too little. We really need people like you to understand how to use them. It's exciting. Think of the massive opportunity. You know, maybe you are a game developer. Maybe you love video games. Why not starting to think how to put together the quantum effects in an amazing video game, the first of its kind? Or maybe you're a student, you want to know more. Then why don't you go to NUS, where they have the Center for Quantum Technologies, which is one of the leading institutions in the world, and is here in Singapore at our doorstep. Or maybe you're a company, and you want to understand how you can integrate quantum, the power of quantum computing into your workflow. Then you should come and talk to companies like us. And the message is, start to be quantum ready. The quantum revolution has already started. The devices are out there. More and more academics are leaving their jobs at the university to launch startups like me. The tech giants are pouring billions of dollars into the technology. It's a really exciting space today, and there's a great opportunity for all of you. So I really want to invite you to embrace quantum computing. Thank you very much.